One of our last lessons in Chapter 4 is something called the second fundamental theorem of calculus. And before I really dive into what that is and how we work with it, I need to convince you the idea of sort of a strange concept. And that is the concept that a function can be an antiderivative. And so let me write that down. What I mean is, somebody could very easily say that f of x is the integral from 1 to x of 3t squared minus 4t plus 1 dt. And I want to take a minute to explain what this is. Really what we need to get at is what does it mean to be a function? Remember, the whole idea behind a function is that you plug a number in and you get something out. So what does this function do, right? I mean, for instance, if somebody were asked to ask you, what does f of 3 mean? Well, that just means that you're going to do the integral from 1 to 3 of the function that we mentioned earlier, right? What if somebody said they wanted f of 5? Well, okay, that means you'll do the integral from 1 to 5 of the function. The whole idea is, suppose that I had an integral like this that I was going to want to plug lots of different numbers into. Like maybe for whatever reason it's my job to do this integral all day long and plug in different values. It would make sense for me to write this function and say, like, look, I don't want to have to write down the integral from 1 to 3, blah, 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 dt, and then the integral from 1 to 5, blah, 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 dt. Instead, I'd rather just say f of 3 and have everybody understand that just means the integral from 1 to 3. When somebody says to me, hey, I need you to compute f of 9, they don't have to write the entire integral from 1 to 9 of this function. They can just tell me, hey, f of 9. And I and everyone else know what that means because I defined a function. I know that was kind of a long intro, but the idea is this is okay and this is normal. As we get a little further into this class, I'll explain more what this means. For now, suffice to say, it's a very normal thing to take an integral and to say that that's equal to a function. Now that I've done that, the next question becomes, what happens when I take the derivative of that function? So for instance, let me move this up and take a look at a new thing. Suppose somebody tells you, yep, I'm making up a function. F of x is going to be the integral from 5 to x. Note, I can change this bottom number to be whatever I want. The integral from 5 to x of, I don't know, t squared minus 3 dt. What happens when somebody asks you for f prime of x? What happens when somebody says, hey, what's the derivative of your function? And for now, I'm going to give you the shortcut for that, and I'm going to explain through the course of this video where that comes from. The short of it is, and you can sort of imagine here, what happens if I take the derivative of both sides? On the left side, the derivative is f prime of x. On the right side, I'm doing the derivative of an integral, or the derivative of an antiderivative, which is, they should sort of cancel one another out. And I'm going to tell you now that this answer will simply be the function inside with x plugged in. So it'll be x squared minus 3. Right? As another example, suppose somebody told you, yep, I'm thinking of a function g of x. That function is the integral from 2 to x of the tangent of t dt. What is g prime of x? What is the derivative of that function? Well, because it's starting from a constant and going up to x, we just take the function inside and rewrite it with an x. So this would be tangent x. Really not a big deal. As one more example, suppose that I had the function h of x, and this was the integral from negative 10 to x of even something crazy like cosine cubed t dt, right? Even though I don't know how to take this antiderivative, if I take the derivative of this thing, if I ask you what h prime of x is, we simply rewrite the function inside with an x plugged in. Cosine cubed x. And I'll admit, these problems get more complicated. There are more weird things that happen. I'm going to cover those in a later video. For now, I want to start with why. Because I imagine you're looking at these three examples saying like, okay, these seem like the easiest problems ever. Apparently, I just have to take the function that's inside and rewrite it with an x. Take tangent t and write it as tangent x. Take cosine cubed t and write it as cosine cubed x. And you're right, the first few problems in the homework are probably going to be ridiculously simple because they're like that. Like I said, they do get a little more complicated, but for now I want to cover why. Like, why does this happen? And I think the best way to do that is in two different ways. One way, I'm going to do it by literally showing you examples, and the second way is going to be sort of a more theoretical method, and I may actually save that for the next video. So I suppose the next section should be called demonstrating the second fundamental theorem through examples. So let's actually take one of these functions before that I mentioned. Suppose I took f of x equals the integral from 1 to x of, let's do 4t minus 5 dt. So I would say that there's a sense in which, and keep in mind that the question here would be asking, what is f prime of x? What is the derivative of that thing? So in some sense, one way to tackle this problem would be to just find out, like literally find out what f of x actually is. Like, this antiderivative should be very easy. The antiderivative of 4t will be, and I'm going to skip the work for it, will be 2t squared minus, and 5 becomes 5t, which we then evaluate from 1 up to x. So then, in order to find out what f of x is, we plug in x first. It gives me 2x squared minus 5x minus, and then we plug in 1, which is 2 minus 5. So we end up finding out that f of x is 2x squared minus 5x, let's see here, plus 3. So yay, this is what f of x is. Now the question is, what is the derivative of that function? And we go back and we look at it and say, okay, well, power rule, we bring the 2 down and multiply it. That gets me 4x. The derivative of minus 5x is minus 5. And the derivative of this constant at the end, because it's just a constant, is 0. And so you notice this thing that I got, f prime of x being 4x minus 5, is really, at its heart, the same function as the original integrand. The original integrand was 4t minus 5. It's simply 4x minus 5 now, because as a part of this integration process, I had to plug in that x, which sort of changed the problem from being in terms of t to being in terms of x. So that was sort of me showing you one example of why this thing works out this way. And again, it should make sense. Think about this process. We had an antiderivative. We took that antiderivative, so we're like, yay, we found the function that this came from. And then what did we do? We took the derivative of that thing to go back, in some sense, to where the problem had come from. So this all justifies this idea of the second fundamental theorem, which simply says that when you take the derivative of an integral, you're just going to get the integrand back with that variable plugged in. In the next video, I'm going to open by explaining another version of how we know this is true, and then I'll actually go through some more complicated examples.